Hey there, Math 1. Welcome to Chapter 3, Section 7. Here we go. In the last section, we talked about symmetry and specifically reflection symmetry. So today, we are going to talk about the other two types of symmetry there are, rotation symmetry and translation symmetry. And we are starting with rotation symmetry, as you can see. So here we go. Rotation symmetry. A figure has rotation symmetry if it can be rotated less than 360 degrees and map onto itself. That is, appear to remain unchanged, right? Some figures have more than one angle measure they can be rotated and remain unchanged. We're going to look at that. So I guess we're going to go right to the first example here. And here's the thing. I know that you don't have this picture on your paper. So you might need to draw something like this as neatly as you can on your paper. It was my fault. I forgot to put it on there. All right, so is the figure at the right a polygon? Last time last section, we looked at what is and is not a polygon. This is got all straight sides and it's closed. It's a polygon. Does it have rotation symmetry? Well, here's the deal. Something has rotation symmetry if there is a point, like maybe there's a point somewhere right in the middle here, and when you spin this thing on that point, if it matches up with itself before it goes all the way around, because all shapes could go all the way around and then match up with themselves, but if it matches up with itself before it goes all the way around, then it has rotation symmetry. And I would claim that when this point starts spinning, and it keeps going, when it gets to here, then that shape will match up with itself again. I'm, of course, assuming that all three of these like legs are the same. And they are. So does it have rotation symmetry? It does. And in fact, I could spin it again. And when that point got here, the shape would match up with itself again. And then a third time would be when it goes all the way around, of course. All shapes when they go all the way around. So it's asking you, if any, what angles of rotation symmetry does it have? All right, so technically, I would like you to write this down. I've tried to change the color. Let's see. So, angle of rotation symmetry. Angle of rotation symmetry. Technically, it is the smallest angle that maps onto itself. And the way you calculate that angle, is by doing 360 divided by the number of times it matches. All right, so this one actually matches 3 times. All right, it matches once when it gets here, it matches a second time when it gets here, and of course it matches a third time when it goes all the way around. So there are 3 separate positions where it would match up. So the angles of symmetry would be 360 divided by 3, or every 120 degrees. The angle of symmetry, the angle of rotation that gives it symmetry, would be 120 and then 240. And you could say 360, but all shapes have 360, and if that's all they have, then they do not have rotation symmetry. All right, so we want to examine the shapes below and identify those that have rotation symmetry. And it's asking you to name the smallest angle of rotation symmetry. You could pause the video if you wanted and then see how you did, or you can just write down my answers, I guess. So this one would actually match up with itself being a regular hexagon. If I spun it around its center, it would match up with itself once, then twice, then 3 times. It would be 360 divided by 6, or every 60 degrees. The kite, no such luck. The rectangle. The rectangle matches up with itself twice, which is every 180 degrees. The square. The square matches up with itself 4 times, which is 90 degrees. Not that guy, not that guy. This guy is 360 divided by 3, which is 60 degrees. Not that guy. Can you spin an isosceles trapezoid around? Nope, don't think so. Parallelogram, though. He's like the rectangle. Right? They're similar. This would also be 360 divided by 2, which is 180. The regular pentagon. So he's going to match up with himself every time the corner goes to a new corner. That would be 360 divided by 5. That's terrible. 72. The circle. Infinitely many times. The rhombus. The rhombus is also matches up with itself twice. When this corner gets to here, it would match up with itself. And the isosceles triangle does not. You cannot spin it around. So there are your basic shapes and rotation symmetry. We got one more, and that is translation symmetry, and we're done. It's a short one, isn't it? Woo! All right, translation symmetry. A figure would have translation symmetry if it is translated so that it maps onto itself. Now, is there any polygon that can be translated, you know, like up some amount and right some amount, so that it's the same as the original figure? Like if I take this triangle and I move that triangle up or down or right or left, is it going to end up right where it started? Well, the answer is no. That would be impossible. How could you move that triangle and have it end up where it started? Unless you went like up 3, down 3, but then you have not moved it. So no, it cannot move. It does not have, I guess I should be saying, it does not have translation symmetry. Right? One more here. Is there any kind of figure? Is there any kind of figure that you can move it and it ends up being in the same place? Well, yes, there is. Haha, you didn't expect that, did you? How about try this? First of all, oops, didn't want to do that. Let's graph a line. Let's graph the line y equals 2/3 x plus 1. So that, of course, has a y-intercept of 1. It's got a slope of up 2, right 3, up 2, right 3. Or I could go the other way, I suppose, if I wanted to draw a nice straight line. And my line would look like that. Boom. Now we're going to translate that line. And we are going to translate that line going x plus 3, y plus 2. We're going to do that translation. So why don't I do this one in orange? So I'm going to start with this point, and I'm going to move it, let's see, y plus 3, that means right 3. I mean x plus 3, sorry. Y plus 2 means up 2. So if I take this point and I go right 3 and up 2, I end up there. And if I take this point and I go right 3 and up 2, I end up there. And look, haha, the same line. Lines actually do have translation symmetry. A line translated by its slope. That is a figure that has translation symmetry. All right, we're almost done. 2 minutes probably. Name all the types of symmetry for the regular decagon below. Now, once again, I have to apologize. I know you do not have this decagon on your paper. You could try to trace it or draw it. Maybe you could even print this page out if you really wanted it. And sadly, my dodecagon got a little piece missing. It got hole punched, I think. So there we go. My decagon is back. All right, so my question is, name all the types of symmetry. Does it have reflection symmetry? Well, you know it does. All regular shapes have reflection symmetry. And if you remember from the last notes, it's got the same number of sides would be the same number of lines of symmetry. So this thing, a decagon, has 10 sides. So it would have 10 lines of symmetry. Yes. And you could get those by connecting angle to angle and midpoint of side to midpoint of opposite side. And I could draw 10 of them if I wanted to, but I'm not going to. How about rotation symmetry? Yes. When this moves to here, it will match up with itself, right? And then it'll match up with itself again when you rotate to there around the center. What is the angle of rotation? Well, that would be 360 divided by how many times it matches. 360 divided by 10 every 36 degrees. And does it have, last but not least, translation symmetry? No, polygons sadly do not have translation symmetry. There you go. Good luck with the homework. See you tomorrow.